In this video, I will demonstrate two common evaluation techniques for single subject design, the acceleration line and the two standard deviation band method. Data analysis in single subject research is based on evaluation of measurements within and across design phases to determine if behaviors are changing and if observed changes during intervention are associated with the onset of treatment. Visual analysis of the graphic display of data is the most commonly used method. Many researchers prefer to use a form of statistical analysis to corroborate visual analysis of time series design, to determine whether differences between phases are meaningful or if they could have occurred by chance alone. Statistical analysis provides a more quantitative approach to determine whether observed changes are real or chance occurrences. In this video, we will examine a combination approach. So visual analysis is used most often to analyze single subject data because it is intuitively meaningful. In contrast to statistical analysis in group designs, this approach focuses on the clinical significance of outcomes. Data collected in a single subject experiment can be analyzed in terms of within phase and between phase characteristics. Data within a phase are described according to stability or variability and trend or direction of change. An analysis of changes between phases is used to evaluate the research hypothesis. Phase comparisons can be made only across adjacent phases. These comparisons are based on changes in three characteristics of the data: level, trend, and slope. Changes in level refer to the value of the dependent variable or magnitude of performance at the point of intervention. It is evaluated by comparing the value of the outcome at the last data point of one phase with its value at the first data point of the next adjacent phase. So we would compare the last data point of the baseline phase to the first data point of the treatment phase. Level can also be described in terms of the mean or average value of the outcome within a phase. Mean levels can then be compared across phases as a method of summarizing change. Means are useful for describing stable data that have no slope, as stable values will tend to cluster around the mean. However, when data are very variable or when they exhibit a sharp slope, means can be misleading. Mean values should always be shown on a graph of the raw data to reduce the chance of any misinterpretation. Trend. Trend refers to the direction of change within a phase. Trends can be described as accelerating or decelerating and may be characterized as stable or variable. Trends can also be linear or curvilinear. A trend in baseline data does not present a serious problem typically when it reflects changes in a direction opposite to that expected during the intervention. One would then anticipate a distinct change in direction once treatment is initiated. However, it can be a problem when the baseline trend follows the direction of change expected during the treatment. If the improving trend is continued into the intervention phase, it is then difficult to assess treatment effects, as the outcome is already improving without treatment. It's important to consider what other factors may be contributing to this improvement. It could be maturation, a placebo effect, a testing effect, or the effect of some other treatment. Instituting treatment under these conditions would make it difficult to draw definitive conclusions. When trends occur in the baseline, it's usually advisable to extend the baseline phase so that we can try and achieve a plateau or reversal in the trend, and then try and identify causative factors. These factors may be useful interventions in their own right and may provide the basis for further study. Lastly, the slope of a trend refers to the angle or rate of change within the data. Slope can be only determined for linear trends. Data analysis in single subject research has traditionally focused on visual interpretation of these characteristics. Unfortunately, real data can be sufficiently variable that such subjective determinants are often unreliable. Although inter-rater reliability of visual analysis is not necessarily strong, the reliability of assessing trend is greatly enhanced by drawing a straight line that characterizes the rate of change. The most popular method involves drawing a line that represents the linear trend and slope for a data series. This procedure results in a acceleration line which describes trends as accelerating or decelerating. You may also wonder why we don't just use inferential tests. Well, there's a few drawbacks to that. One of them is a limited number of data points. If we only have a handful of data points in the treatment phase and the baseline phase, our n becomes the number of data points. So if we're going to do a t-test on these two phases, we'd only have 5 perhaps data points that we can compare, and that will violate one of the basic assumptions of inferential tests as far as having an adequate sample size. Another has to do with the limited generalizability. When we have single subject research, we're only gathering data on a single person, on one individual. And if we then use inferential tests on that data, we're violating, again, one of the assumptions of inferential tests. Inferential tests are designed to infer something about a population using a sample. So if our sample is only one person, one individual, then there's probably not enough variability or maybe too much variability in that one individual to then make inferences about the population. And last has to do with serial dependency, and this is not uncommon in time series design with individual people because the data points are dependent on each other. In other words, they're interrelated to each other. So the value of one data point is related to what the value of the previous data point was. And so when we have that interrelatability, that intercorrelation among data points, that can cause some difficulties with some of the inferential tests that we do. So here's some examples of some different trend lines which we can observe the different characteristics we just discussed. So as we look at the first example here, example A, we can see that difference in the level. So here's the last data point of the baseline and the first data point of the treatment phase, and we can see there is a definite difference in level. If we look at the example just below, we can see there is no difference in the level. So in the first example, there was a definite change in the outcome with the initiation of treatment. In the second example, there was no real change with the initiation of treatment initially, and as you can see later on that there was. The next is the trend. As we can see how the data points are arranged, we can start to pick out different types of trends. So as we can see in example A here, in the baseline phase, we can see that even though there's some up and down movement of the data points, the basic trend is a straight line. But if we look at the example just below, we can see we have a basic downward trend in the baseline. Now the last thing we can look at is the slope, and that has to do with the angle of the trend that might be occurring. Now in this lower example here, example E, we can see in the baseline we have a downward trend, but it's a fairly shallow trend. If we compare that to the downward trend in the treatment phase, which is much sharper. So as we look at these graphical displays of the data, we can take those three characteristics, trend, slope, and level, and we can start to make some basic interpretations of what's happening in the treatment phase compared to the baseline phase. Now the acceleration line method is what we'll talk about first, and as I mentioned before, this is a basic graphical way of representing trends in the data. So we're using lines to represent linear trends and slopes of the data point. So acceleration line is used to estimate the trend within a data series. Although in this demonstration that we're going to go through, we're only going to go through the process for the baseline data. In practice, a separate acceleration line can be computed for each phase in the design. And so again, the acceleration line describes data relative to our three characteristics, level, trend, and slope. Now we use what's known as the split middle line and the binomial test, which is an inferential test to assess the null hypothesis that the intervention has not changed the relative positions of the data points across the phases. So we're going to use a combination of visual interpretation and hypothesis testing to make some decisions about what's happening in the treatment phase relative to the baseline phase. So at this point I'm going to switch over to Excel and show you how to actually construct a acceleration line, a split middle line, and then perform the binomial test. So here we are in a basic Excel spreadsheet, and what you'll notice across the top here are our data points. So the first row represents what I'm calling the session number or the observation. So we have 20 observations. As you can see, these are numbered in ascending order. In the row below that is the outcome. the actual value that I measured for my outcome. And again, your outcome can be anything numeric. And so what we're going to do is we're going to create a line graph that's going to represent the data in the baseline phase and the treatment phase. And you'll notice I have a blank column here between the baseline phase and the treatment phase, and this is going to actually separate the data out for us in our line graph, so it'll make it easier to differentiate between the two phases. So let's go ahead and create that line graph first of all. So we want to go to the Insert menu and select Line, and then we're going to choose the one in the upper left-hand corner, which is the basic 2D line graph. Okay, now we're in the Chart Tools section. The first thing we want to do is select the data that we want to include in our line graph, and we're going to go ahead and click this Select Data button. And then we basically highlight the outcome values only, so it's just going to be that row. We don't want to highlight the header. And then once we've highlighted that, we click OK, and as you can see here, we have our line graph. So I'm going to do a little bit of formatting. I'm going to make this a little bit bigger, and then I'm going to go ahead and delete the legend here by clicking on it and then clicking my delete button. And now I'm going to go ahead and make it larger so it'll be a little bit easier to see as I go through my Now my first step here in formatting this is I want to draw a vertical line that's going to differentiate and delineate my baseline phase from my treatment phase, so I can visually see where each phase ends and or begins. So what I want to do is click on the Insert menu, and I want to insert a shape. And I'm just going to click a basic line, and I want to draw a vertical line from the top of my graph down to the bottom of my graph. And this is basically just, again, delineating the difference between my baseline phase and my treatment phase. Okay, once I have that in place, I can go ahead and format that a little bit. I'm going to make it a different color from my data line, and I'm also going to make it thicker by clicking on the weight of the line and let's make it a 2 1/4 point line. So now I can visualize the difference between my two phases. Here's my baseline phase, here's my treatment phase. Now the next thing I can do to my lines to make them a little easier to use as I draw this acceleration line is I want to have a data point, a shape that will actually delineate the value at each data point on my line. So what I want to do is left click on my line, and then I want to right click on the line and then click Format Data Series. Okay, and the first thing I want to do is choose a marker. So this is going to be that shape that's going to delineate each data point. So I want to click Built-in, and then I want to choose my shape. I prefer circles. Okay, I'm going to make these a little bit larger. Let's make them a 9. And then we go ahead and click Close. And so now I've got data points marked with some sort of a shape, so it's going to be a little easier to see things. Okay, so we're going to draw the acceleration line. We're going to do it just for the baseline data, as I mentioned, but you would do it for the treatment data as well. So I'm just going to keep it to the baseline data for demonstration purposes. So the first thing we need to do is we actually need to separate our baseline data into two parts, a first half and a second half. So we can then draw points that we can base our acceleration line on. So the first step is to count the number of data points in my phase and then divide these points into 2 equal halves with a vertical line. So I've got 10 data points here, so I know I'm going to have 5 in the first half of my baseline and 5 in the second half. So I'm going to go ahead again and just draw a basic line that's going to separate out the 2 halves of my baseline phase. And again, this doesn't have to be a real complicated or fancy line. So now I have my baseline phase separated into 2 halves, 5 on each point. If you've got an even number of data points, or sorry, an odd number of data points, then you'll have to draw this line to separate them in half, and it'll have to go directly through your middle data point. All right, so now that I have my baseline divided into 2 halves, I need to come up with 2 values for those 2 halves of the data point. I need to find out the median score for the first half of the baseline and a median score for the second half of the baseline. And so what I've done is listed the baseline scores from the first half, the first 5 data points. You can see that matches up with my first 5 data points, and then the data points from, the second half of my baseline phase. And then I did an insert formula that gave me the median score for each half of the baseline phase. So I simply just went to I went to formulas and inserted the function for the median, and it calculated the median for each half. So that's going to be an important thing for me to know. So let's go ahead and use that median now to begin drawing our acceleration line. So let's start with the first half data. So once I know my median score, I want to insert a new line, another line, that's going to be horizontal, that's going to go through, or it's going to mark the median line. So that's going to, in this case, that's going to be 4 for the first half of the data. So I'm going to draw this new line that's going to go through or be associated with the median score of 4, which makes it easy because I've got this line of 4. I'm going to do the same thing in the second half data point, but it's got a second half of the baseline phase, but it has a different median score. So I'm again going to insert a line, but now this is going to be at the data point of 5, and I'm going to bring it across like so, and it happens to go right through those last two data points. Okay, now my next step is to find the middle score in the series. So in the first half of my baseline phase, I have 5 data points. So I want to find the data point that was the third data point collected. So that's going to be this data point right here. So because I have 5 data points, I'm going to draw this vertical line through the third data point. If I had an even number of data points in each half, the line would be drawn directly between the 2 middle points. So that's my next step. I'm going to take a vertical line and draw it right through my middle data point, which is the third data point in the first half. And I do the same thing in the second half. I've got, I'm going to insert another line. I'm going to do it through the third data point of the second half. Okay, so now you can see here I've got 2 kind of crosshairs that I've created. And I'm going to use these now to draw the acceleration line. Okay, now to draw the acceleration line, I'm going to insert another line. And to start this line, what I have to do is start at my first data point. So that's going to be the left side anchor of my acceleration line. And then I want to try and draw that line so that it goes through my 2 crosshairs as best as I can make it. So I want them to come as close to those 2 crosshairs as I can. Now as I'm doing this, what I want to try and do is make sure that I come as close as I can to those 2 crosshairs. If I can't touch them both, fine, but I want to try and find the point at which I can come as close to the both of them as possible. And this appears to be about that line right there. And so now I've drawn that. So that's my acceleration line. Now one way we have to look at this to make sure we've drawn the correct acceleration line is we need to see if this line is also what's known as the split middle line. And so that's the line that basically divides the data points in half vertically. So do we have the same number of data points above the acceleration line as we have below it? So let's count this out. So below we have 1, 2, 3, 4 points, and above we have 1, 2, 3, 4, 5. We don't count the data points that are on the line. So as you can see, I've got 1 more data point above the line than I do below it. So my acceleration line isn't quite in the same right spot. It's not the split middle line. So what I have to do is adjust my line slightly so that I have an equal number of data points above and below. And again, we don't count the data points that are on the line. So now I've got 1, 2 data points on my line, and I've got 1, 2, 3, 4 above, 1, 2, 3, 4 below. So now my acceleration line and my split middle line are the same. They won't always be the same. Very often they will be the same. But in this case, they weren't exactly the same, so I had to adjust my line slightly away from one of the crosshairs to make it the true split middle line. So now this is the line that demonstrates the best trend in the data. Another way to think about it is it represents a measure of central tendency of the trend. So the split middle line divides the data within a phase into 2 equal parts. So it represents a median point within the phase. So now the split middle line can be used to compare the trend of data across 2 adjacent phases. So let me show you how that will work. So before I do that, I'm going to clean this area up a little bit. So I'm going to take out these lines, these horizontal and vertical lines that I drew to help me draw my acceleration line, to clean things up a little bit. But I'm going to keep my acceleration line. So what I would basically do is just click on a line I want to get rid of, hit my delete button, and I'm going to go ahead and go through that process for these lines that I drew to create my acceleration line, just to make my graph look a little neater and cleaner. Okay, so now I still have my acceleration line. Now, so what I do in order to now make a comparison between the baseline and the treatment phase using my acceleration line or my split middle line is extend this split middle line into the treatment phase. So I'm going to again insert another line, and I'm going to start it where my acceleration line ended at the end of the baseline phase, and I'm now going to extend it into the treatment phase. And I have to eyeball this, and I want it to have the same slope that the acceleration line has, and I may have to eyeball that a little bit, but I want it to basically continue on in the same pattern, the same slope from the baseline phase to the intervention phase. And so now basically my split middle line extends out into the treatment phase. Now I can clean this up again a little bit to make it look a little bit more effective. So I'm gonna make this a different color. I'm gonna make it red, and I'm gonna make it a little bit thicker so that I can see it a little bit better. Okay, so there's my acceleration line, and then as I extend it out to the treatment phase, I'm gonna make this one red as well, but I'm gonna make it a dashed line so that I know that it's not the acceleration line, it's the extension of the split middle line. Okay, so now I have my acceleration line and my split middle line extended out into my treatment phase. So how do we evaluate this? Well, if there is no difference between the phases, then the split middle line, the dotted line for the baseline data, should also be the split middle line for the intervention or treatment phase. In other words, 50% of the data in the intervention phase should fall on or above that dotted line, and 50% should fall on or below it. If there is a difference and the treatment has caused a real change in observed behavior, then the extended baseline trend should not fit this pattern. So as you can see here, my treatment data does not fit that pattern. There are 9 data points above the acceleration line or split middle line and 1 below it. It's not 50-50. So what I would be able to conclude then is that the treatment created a significant change in the outcome, because I'm not seeing the same trend here in the baseline phase in the treatment phase. And so I can conclude that the treatment appeared to have a significant effect, or appeared to have an effect, and then it appears to be creating some meaningful change. Now, statistically, we can continue to test this idea that we have meaningful change. And so now we can propose a null hypothesis, which states that there is no difference across phases. That is, in other words, any changes observed from baseline to the intervention phase are due to chance, not the treatment. And so in order to test that hypothesis and further provide evidence that what we're seeing with the split middle line is a true occurrence, we're going to use something called the binomial test. Now this binomial test, which we're going to test the null hypothesis with, is used when outcomes of a test can be treated as dichotomous. So in this case, data points can either be above or below the split middle line. So to do the test, we're going to need to know a couple of different things. We're first going to need to know the number of points in the intervention phase that fall above the split middle line or below the split middle line. And we're going to ignore points that fall directly on the split middle line if any of them do. Okay, so in order to run the binomial test, we're going to need to go to the Formulas tab. We need to click on. Okay, so we need to go to the Formulas tab, and we're going to do insert function, and we're going to search for the binomial test. And it is designated as binom.dist. This is the binomial test. And we're going to go ahead and click on OK. Now the first thing it needs to know is the number of successes that we had. And we're treating a success as any data point that's above the split middle line. And so we know that we have 9 data points above the split middle line. And so we can go ahead and click or enter in the value of 9. Now the number of trials is the number of data points that we actually collected data on. In this case, that was 10. So the number of trials is 10. The next thing we need to enter in is the probability of success on each trial. So we know this is a dichotomous outcome. They're either above the split middle line or they're below. So the probability is 0.5, 50%, 50-50, like flipping a coin. Okay, the last thing we need to do is include in the cumulative box here what our hypothesis is. If we're testing a null hypothesis and we want to enter in the word false, in other words, we think there won't be any successes. Okay. Once we've done that, we click OK, and then in our outcome box here, what we're going to see is the probability, a p-value, that the outcome that we're seeing is due to chance. So we're going to use the conventional upper limit of p is equals to 0.05, and so any probabilities that are in this box that exceed this value are considered not significant. That is, the observed pattern could have occurred by chance. In this example, the probability associated with the test is much less than 0.05 and therefore is considered statistically significant. So the pattern of response in the intervention phase is significantly different from the baseline. So we can make the conclusion that the treatment created a statistically significant change in the outcome from baseline to intervention. We have evidence of that using the split middle line, and then we also have evidence of that using the binomial test. So if our null hypothesis would be that the treatment would not be effective, would not create change, that the outcome would have the same values in the treatment phase as they would in the baseline phase, we can reject that null hypothesis and say the treatment did have a significant effect. Now the next method we're going to learn about, and another useful method that relies on visual assessment as well, is the 2 standard deviation band method. This process involves assessing the variability within the baseline phase by calculating the mean and standard deviation of the data points within that phase. And then a trend line identifies the mean, and we would also have additional lines place 2 standard deviations above and below the mean. So in order to calculate this, we need to calculate the mean of the baseline scores, the standard deviation of the baseline scores. Then we would double the standard deviation and then add it to the mean for our upper band line and then subtract it from the mean for our lower band line. Now once we've done that, and I'll demonstrate that in Excel in just a minute here, if at least 2 data points from the intervention phase fall outside of this 2 standard deviation band, the intervention is then considered significant. So what we'll have to do is construct the bands, the lines, and then examine the intervention phase data points relative to this 2 standard deviation band. So here we're back in the same Excel data file that we were in before. We have the same 10 data points that we were working with before, and we still have our original line graphs for the baseline phase and for the intervention phase. So what I've done is I've created another column for the baseline phase data points, and then I've inserted formulas to calculate the mean or average of the baseline data points, and then the standard deviation of the baseline data points. So what I need to do first is create my center line that represents the mean of my baseline data points. So I'm going to go to the Insert menu, and I'm going to insert a shape, and I'm going to insert a line. So I want to find the location that is as close as possible to this mean. So right about here would be 4.6, and then I'm going to create a line that's going to go all the way across the graph, and I want to make sure this it's parallel, it's truly horizontal. And then there's my line. So I'll do a little bit of formatting on this to make sure I can differentiate it. So I'm going to make it red, and I'm going to make it also a little bit thicker so that I can differentiate this as my mean line. Okay, so the next thing I need to do is insert and draw my two standard deviation lines. So I took the standard deviation that I calculated, 1.4, and I doubled it to 2.8, and then added that to the mean of 4.6, and that gives me approximately an upper band of 7.5. So I'm going to do the same thing that I did with the mean. I'm going to draw a line. Here's a 7.5 mark, and I'm going to draw that line and make sure it is as horizontal as I can make it all the way across the graph. Now this one I'm also going to turn red, but I'm going to make it a dotted line. So again, I can differentiate that that is the upper two standard deviation line. I make that a dotted line. So again, that's our upper two, so that's two standard deviations above the mean of the baseline. And I'm going to do the same thing for the lower end of the range. So I took my standard deviation, doubled, and I subtracted it from the mean, and that gives me my lower band, and that's going to be 1.7. So I'm going to go ahead and insert another line, find the 1.7, again approximating that as best I can, and moving this line horizontally across the graph. And I'll again format that to be red and dotted. Or a dashed line. Okay, so here's my two standard deviation band. So again, the thick red line denotes the mean of the baseline scores, and then the upper and the lower lines represent the scores that are two standard deviations from that mean, above it and below it. So now, as I mentioned, these lines are then extended to the intervention phase, and our criteria for deciding if the treatment had a significant effect would be if at least two consecutive data points in the intervention phase fall outside of the two standard deviation band, whether it's above it or below it. The changes from the baseline to intervention are considered significant. So as you can see, our mean response was here about 4.6, and our upper band was 7.5. As you can see, only one data point from the intervention phase falls within that two standard deviation band, and the remainder are outside of that band. So we have basically 8 consecutive points that fall outside of that two standard deviation band. So the 8 points in the intervention phase fall above this band, so we could therefore conclude that there was a significant change from the baseline to the intervention phase. So in summary, what we've learned to do in this video is learn how to take single subject design data, create a line graph so we can visualize the change that can be occurring in that data from baseline phase to intervention phase. And we talked about different characteristics that we can use to describe those data points in relation to one another as well as within a single phase, and that's the trend, the slope, and the level. And then we learn how to do the acceleration line and the split middle line that can help us start to make some decisions about how the data points in the treatment phase may be different from those in the baseline phase. We learned how to test the null hypothesis using the binomial test. And then we learned the two standard deviation band method. This was another visual tool that we can use to determine if data points in the treatment phase appear to be significantly different from the data points in the baseline phase. So hopefully you found this informative and useful, and good luck using this technique on your own.